Okay, we're going to do 6-1 today. Our objectives are the student will be able to graph exponential growth and decay functions and then use exponential models to solve real-life problems. So an exponential function can be written in the form of y equals ab to the x, where a is not equal to 0 and b is greater than 1. What really makes an exponential function is when we've now put the variable in the exponent. So if a is greater than 0 and b is greater than 1, then it is an exponential growth problem, and b is the growth what's called the growth factor. The parent exponential growth function is y equals b to the x. Remember, our parent function is always the simplest function we could have, and so that would be as simple as we can get, where a is 1 and we just have b to the x. If a is greater than 0 and b is between 0 and 1, then it's exponential decay. And so these are the two main things we want to understand on this, is what exponential growth is, and that's when a is greater than 0 and b is greater than 1. And then the difference is, when b is between 0 and 1, it's exponential decay. Those are the two main things we're going to be dealing with on this. So, if we look at the concepts of growth and decay on page 296 at the core concepts, so we're going to go to the textbook. And again, it gives our definition here, but I want to look at what it has here. It has what we just talked about, but I want to look at the graph of this. This is exponential growth graph. An asymptote, we've talked about that before. Remember, an asymptote is a line that the graph approaches but never crosses. And on this you can see it's going to get closer and closer to the x-axis, but it's never going to cross it. This way it's going to go up and it's going to go up forever, but it's going to get closer and closer to the x-axis on this parent function as we go to graph this. So that again is an asymptote, which it's a line approaches but never crosses. So if we go back. So the first thing, example number 1, determine if the function is exponential growth or decay and then graph. And so the steps that you're going to go through, I've got 4 steps for you. First of all, identify the base, what b is. That will tell you whether it's a growth or decay problem. Make a table of the values. Plot the points, and then draw the graph. Now on the assignment, I'm not actually going to have you draw the graph. I'm just going to have you make the table of values. I'll assume that you could plot the points. So if we look at the examples that we've got here, these are the first 2 examples. So the first thing we're going to do, identify the base. Remember, base is b, so in this case our b is equal to 2. So if we go back and we check this, if we go back, we know that it's greater than 1, and so this is a growth problem. And then we can just go to the Desmos calculator. We go to the Desmos, and we type it in. Y equals 2 to the x power. We get this graph. Okay? And then we can go to our table and get our values. So we get -2 is at 0.25, and they plot them on the graph for us, and you can see they've plotted them there. And so if you were actually graphing it, you would then plot those points and then draw your graph through it. And again, it would approach this 0, and you can see because lines have width, it actually looks like it touches, but it would never cross this no matter how far out I went. We get closer and closer to 0, but never get there. So all you're going to have to do on the assignment is show the table. You don't actually have to take the time to graph those. But if we were to do this, so at -2 we're at 0.25, at -1 we're at 0.5, 0, 1, 1, 2, 2, 4. So now if I was to graph this, I would go back, and so at -2 we're at 0.25, so we're really close here. At -0.5, or at -1, we're at 0.5. So again, at 0, we're at 1. At 1, we're at 2. And at 2, we're at 4. A little easier when we get up here. But you can see it's going to go up in a hurry, and it's getting closer and closer to this line, but never cross it. Okay? So now when we look at this one, our b value is 1/2, so that's between 0 and 1, so that is a decay problem. And so now again, if we go back to the Desmos, the change is, if we go back, let's just delete this. So y equals, put that in parentheses, 1 divided by 2 to the x power. So we get our graph, now you can see the decay is going to go the other way. Before it was increasing, now it's going to be decreasing. Again, all we have to do is go to the table and get our values, -2, 4, -1, 2. And again, you would plot those if you were doing the graph and connect them to get an estimate of what the graph would look like. So, what I'd like you to do now is to go ahead, determine whether this is growth or decay on your own, then come up with the tables. You don't actually have to do the graphs. So I want you to determine growth or decay and then come up with the tables. So you can pause it here, go back and check that, and then come back and see how you did. So if you did this one, our b value is 4, so that's growth. In this case, our b value is 2/3, and so that is decay. Here, 0.25 is our b value, and so that is decay. And 1.5 is our b value, and so that is growth. And then you should have on the graphing calculator, we go to the Desmos, we can just type that in. So the first one was y equals 4 to the x power. And so then all you had to do was get the table, and you should have had for -2 point, on these just round to the nearest hundredth, so 0.06, -1, 0.25, 0, 1, 1, 4, and 2/16. That would be the first one. The second one was y equals. Now, when you have a fraction, you need to put it in parentheses because if you didn't put parentheses, it's only going to affect one of them. So now we've got this. So again, we simply go to table. And so for -2, you'd have 2.25. For -1, 1.5. For 0, you get 1. 1, you get 0.67. And 2, you would get 0.44. So you should have gotten that. The third one was, now it said f of x, but f of x, remember, is just like y. So y equals 0.25. Now they had parentheses on this. Technically you wouldn't need it for the decimal, but just write it the way it was. And so now again we've got that. We go to table. You should have gotten -2/16, -1,401, 1.25. And 2 would be 0.06 if we round to the nearest 10th or 100th. And then the last one was y, or again f of x, so y equals 1.5 to the x. Again, we've got our graph. It reaffirms that it's growth. And so now we go to table and you get your values. So -2 is 0.44. -1 is 0.67, 0 is 1, 1 is 1.5, and 2 is 2.25. So, those are fairly easy to do. Again, determine what b is so you can find the growth or decay, and then just get your tables. Next, we're going to look at some exponential models. In real life, quantities increase or decrease by a fixed percent each year. The amount y of such a quantity after t years can be modeled by the formula. And then we have two formulas, whether it's growth or decay. Growth is y equals a and then in parentheses 1 plus r to the t power, and for decay it would be y equals 1, or excuse me, a, and then 1 minus r to the t power. So, in these, a is the initial amount in both cases. R is the rate of increase over here, because we're going to look for an increase. R here is the rate of decrease. And then 1 plus R is your growth factor, and 1 minus R is your decay factor. Now we'd like the things we invest in to have a growth factor. Like homes usually have a growth factor, they go up in value. Cars usually have a decay factor, they go down in value. So we're going to look at problems involving this. So we're going to look at examples 2 and 3 and MP 5 and 6 on page 298 in the textbook. So let's go to the textbook. Go to page 298. So, it says solving a real life problem. The value of a car Y in thousands of dollars. So understand that this chart, this 30 would be $30,000, can be approximated by the model y equals 25 times 0.85 to the t power, where t is the number of years since the car was new. Tell whether the model represents exponential growth or exponential decay. Now the way we can tell that is, remember our formulas were 1 plus r and 1 minus r. So if this number is less than 1, then it's a decay problem. So in this case, we can also find out what r was, because it would be 1 minus r equals 0.85. So if you subtract 1, you get negative r equals negative 0.15. And so our r in this case is 0.15, or if we change it to a percent, 15%. Okay? So we know that this was a decay problem. Okay? Identify the annual percentage increase or decrease of the value of the car. That's what we did here. We found out the actual rate of decrease is 15%. And then it says estimate when the car value will be $8,000. Well, we can do that on the graphing calculator. You can just type in the equation on the Desmos, and then let's just draw that one in. Y equals 25 times 0.85. Y equals 25 and then times 0.85 to the x. So we've got this graph here. And so now we can just put it on here. We want to know when the car gets to $8,000. So there it's at 7.975, right about 7 years. That's 8,000 and so $8,014. So it's really close at 7 years. So if we go back to the textbook, it says it's about 7 years because it was 8,014 exactly at 7 years. So you can just use the trace factor and find out approximately how many years it would take before it gets to 8,000. Again, on that you can find out how many years before it gets to any price by just using that trace function. So now, if we look at example number 3, writing an exponential model. It says in 2000 the world population was about 6.09 billion. During the next 13 years the world population increased by about 1.18% each year. Write an exponential growth model giving the population y in billions t years after the 2000. Estimate the world population in 2005. So, we know our starting point was 6.09. That's our A value. And then 1 plus, it's going up 1.18% interest. Now remember, when you take a percent and put it in an equation, we have to move that decimal 2 places to the left. So it would be 0.0118. And then to the t. So this would be our equation. And then it says estimate the world population in 2005. Well, all we have to do now is plug t plug the value of 5 in, so we've got our equation there, and it says when we plug in 5, we end up at about 6.46 billion people in the year 2005. Then it wants us to estimate when it will get to 7 billion people. So again, now if we go to the chart, or the calculator, 6.09, so we can get that graph. And then we want to know when it's going to get to about, is it 7 billion? Let's check. When is it going to reach 7 billion people? So, we just go here, and we're looking for 7. .953, 6.97. So it's going to be, there we go, 11.9, so about 12 years. And so we come up with that it's going to be approximately 12 years before it gets to that 7 billion people. So now, I'd like you to try these next two, and then you can come back and see how you did. So it says in example 2, the value of the car can be approximated by the model y equals 25 times 0.9t. Identify the annual percentage of decrease in value of the car and estimate when the value of the car will be $8,000. And then for 6, if example 3, what we just did, assume the world population increased by 1.5% each year, write an equation to model the situation and estimate the year when the population was 7 billion. So go ahead and pause the video here and try those two. Now, if you did this, so on this one, if you put in the equation y equals 25.9t, so again, since that is less than 1, it's a decrease. And again, all you had to do is take 1 minus 0.9, and that would give you that it was a 10% decrease. And so now we know it's going down at 10%. And so then they want you to identify when it'll get to 8,000, and if you plug that in, hopefully you got that it was 10.7, or about 11 years when the car would get to the value of 8,000. Then in example 3, you would rewrite this equation and do the exact same equation, but it would be 1 plus, move the decimal 2 places, 0.015 t. And now they want you to estimate when it would get to 7 billion, and if you did that correctly on your trace function, it ends up being about 10 years. So about 2 years sooner, with an increase from 1.18% to 1.5%. So next I want to look at example number 4 on page 299. So let's go back to the book. So if you want to look at example number 4, it says rewriting an exponential function. Okay? So it says the amount y in grams of radioactive isotope, chromium-51, remaining after t days in years, in t days is y equals a 0.5 t to the divided by 28, where a is the initial amount in grams. What is the percent of chromium-51 decays each day? So, have to look at this carefully. So, this is A, and then 0.5 t divided by 28, where again, t is the number of days. And so what they do is they take this equation and they break it up. So they break up the t divided by 28 into 1/28 times t. Okay, because again, remember, a power to a power we multiply, it'd be the same thing. So now what they do is, now that we've got this, they take 0.5 to the 1/28th power, and that comes out to be the decimal 0.9755. Okay? So now we can find out what this value would be by just changing it to 1 minus 0.9755. Okay? To find out, because it's less than 1, right? So if we were to do the formula, let's go ahead and show the formula. It would be 1 minus r equals 0.9755. And then you would subtract 1 from both sides and get negative 0.0245. And since it's negative r would be 0.0245. So all you do is the other way to do it is just take this and subtract 1 to get that value, 0.0245. And so now we've rewritten the formula from this form into the form y equals a times 1 minus r to the t power. So it's a way to convert it from an exponential form into a growth decay formula from the original one. So if we look at that, this next part, we're going to look at compound interest. So compound interest, consider P, which is the initial principal, deposited in an account that pays interest at an annual rate R, expressed as a decimal. Compounded n times a year. So that's how many times they're going to calculate the interest. They can do it monthly, they can do it quarterly, they can do it semi-annually, which would be every half year. They can do it daily. We're going to look at that. So it says the amount A in the account after t years is given by the formula A equals P times 1 plus R divided by n. Remember, n is the number of times that they're going to compound it yearly. And then to the n times t power. So we're going to look at example number 5 in the textbook. So it says you deposit $9,000 in an account that pays 1.46% annual interest. Find the balance after 3 years when the interest is compounded quarterly. So quarterly means 4 times a year. So we now know our initial amount, our P, is 9,000. We know our rate is 1.46. So again, in the problem, we have to change that to a decimal, so 0.0146. And we know that we want to know after 3 years, so the time is going to be 3. And the interest rate is going to be compounded quarterly, so our n is going to be 4. And so they just plug it into the formula, and it comes out that at the end of 3 years, you would have $9,402.21 in the account. So your interest, you would have made $402.21 after 3 years in that account. And that's if it's compounded quarterly. So now if we look at the monitoring progress, it says the amount Y in grams of radioactive isotope iodine-123 remaining after T hours is given by the formula Y equals A times 0.5 to the T divided by 13, where A is the initial amount in grams, what percent of the iodine-123 decays each hour. So now they want us to convert this back to the formula 1 minus R to the T. So we're just going to go ahead and go through this. So we're going to rewrite this, our formula. And we're going to put it to the 1/13th power and move that T outside. And so now we're going to calculate that 0.5 to the 1/13th power. And if you do that, you get A is 0.9481 to the T. Okay? So again, if you're doing on the Desmos, I'm just doing 0.5 0.5 to the 1/13th power. Oops. So you get that 0.9481. Okay? So we've got that 0.9481. And let's go back to the textbook. So that's where we got this 0.9481. And so now we want to write this formula correctly. So again, all we do is we take and we subtract. So that's going to give us that our R value is 915, so 0.0159. So our formula would be y equals A times 1 minus 0.0519 to the T power, to change it back into that form. The last one here, it says, what if in example 5, the balance after 3 years of interest was compounded daily? Okay, so now they want us to go back up to this one. Instead of doing it quarterly, we're going to do it daily. And there are 365 days in the year. So now we would plug this in. And so it would be 9,000 times 1 plus, our rate's not changing, over 365, and then times 365 times 3. So if we put that in the calculator, so y equals 9,000, 1 plus, it was 0.0146 divided by 365, and then 365 times 3. Actually, we can just take out that y because and we get $9,402.95. So if we go back to the textbook, 9,000. So you end up, because it's compounded daily, you get a little bit more interest. Not a lot, but a little. So the more often it's compounded, the more interest that you will get. So, the assignment is page 303 through 37, the odds, skip 25. Again, you don't need to graph, but do need to show your table, so you're going to have to put that on paper. So we're going to try this as where you watch it on the video. So you've watched the lesson, now you don't need to do anything except bring in the paper that shows that you've taken the notes on this, and then we will have 90 minutes in class to work on the assignment. I'll answer questions, but please, hopefully this made sense. Parts that don't, be ready to ask questions about it when you come into class.